Hello, and welcome to this low-level JavaScript series, where we're building what I think will be the world's first RISC-V processor on an FPGA using the TypeScript programming language. And we're actually on episode 11 of this series now. And at this point, if this is your first time viewing, we're building in the beginning an emulator which serves essentially as the design document for the hardware that we will build. And the emulator that we're building is very low level. It simulates the pipeline, it simulates clock cycles, it simulates register transfer level mechanics, basically. So it allows us to essentially do the actual design of the CPU in a nice, easily debuggable, inspectable way before we move on to hardware. And we're coming to the end of the emulator's journey, which is a really exciting moment for me because this is a project that's been going on for a while, and I'm really keen to actually start with the hardware soon. But there's just a couple of things we need to resolve, and one of those things, or sort of a group of those things, we're going to tackle today, and then the sort of final part, which is also an important part, we'll tackle in the next one. So today what we're going to tackle is finishing off the last instructions. At the moment there are just 3 instructions, I believe, that we haven't implemented. They're actually all pretty easy now that we have the basis that we laid down in the last episode. So that's one of the things we're going to be doing. We're also going to be taking a look at the M status register, because when we take an exception or we take a trap, we actually need to sort of update our status in the status register a little bit. And we weren't doing that before, and well, that's something we can do. It's a relatively small thing that we have to take a look at there, but it's basically going to be, it's to do with being able to take multiple exceptions sort of nested together. So we kind of need to save a little bit of state when we enter an exception handler because of that. We're also going to be implementing a reset mechanism. This is something probably should have done way back in the beginning when I first made registers, but it won't take us very long to do it now. Essentially, in hardware, in almost all hardware, when you have registers, there'll be another signal that comes in, which is a reset signal, and that will kind of bring the register back to its original value. And you have synchronous resets and asynchronous resets and all this different kind of stuff. But essentially what we're going to be doing is building in kind of a way that we can reset the state of any given register in any given pipeline stage in any hardware module. That's going to be something we're going to be doing. So it's quite a useful part. And maybe if we have time, although I'm not optimistic about the time, so I won't make any promises, but maybe if it seems like that all goes really quickly, then we'll take a look at adding just a couple of other exception triggers that we can find throughout the code. Because right now we're only triggering on the load address misaligned. When we detect that a load address has been misaligned, then we can take an exception. But we could easily do the same thing for a store, for example, or if an instruction fetch was misaligned or something like that. So there are a couple of different exceptions that we could realistically take in the same way that would not be a large added complexity. But we'll see about that. Follow-up business. So in the meantime, there were a couple of things that I did between now and the last episode that I also talked about in the last episode that I would probably do. Well, the first of these is a relatively small thing, but I renamed the bootloader from bootloader.s, and actually it's not really a bootloader, that's kind of the whole point. I renamed it to crt0.s, and that's kind of a very conventional thing in when you're dealing with this sort of lower levels of C and like messing around with the linker yourself. This crt0 is basically a well-known thing. It's apparently also known as C0. It's a set of execution startup routines linked into a C program that perform any initialization work required before calling the program's main function. And that's exactly what our bootloader.s file was doing. So I'm just following convention here and calling it that. So if we actually go and look at what our CRT0 script does, it basically sets up the reset vector. It sets up the start routine, which is setting the stack pointer, copying an uninitialized, or copying rather initialized variables to RAM, and then jumping to the main code. So it's exactly what the CRT0 is doing. So let's follow convention in that sense. And I also simplified the vector table. It's not a huge difference, but it's actually quite a meaningful one, and I should have done this in the first place because I know that this is how it's done in other architectures, but for some reason I did it in a slightly different way. So previously what we had is that the vector table was actually just a table of addresses, and what I've done is to change that to be a table of jump instructions. So there's basically the table has become a function, and well, it's only a function in the very barest sense of the word, because we're using these GCC attributes to basically say, hey, don't generate any special code around this. I'm just going to drop a block of assembly in here. So we've given it a name, we're calling it a function, but it's not really a function. So what we have is just a big table of jump instructions, and it corresponds exactly the same as it did before. So we're just saying, hey, jump to this function, that's the first one in the list, and so on. And the reason that this is actually better is because it simplifies when we need to take a trap, or take an exception, take a trap. It kind of makes the whole process easier. There's actually one less clock cycle involved in us getting to that exception. And also the CSR, the trap hardware module that we designed in the last last episode, it has one less. It doesn't have one less state here, but you can notice that we actually just load up the address, and we can just jump straight to that. We don't have to look into memory to figure out let's actually go and read the thing in memory at that table. What we can actually do is just jump to this address, which will cause a second jump to happen. So I hope that's clear. Before, what we had to do is basically say, here's the address where we're going to go and find where we need to go to, and then we would load it from memory, and that meant the trap module had to be connected to memory, or the bus at least. And now we don't have to do that. We can just jump to that address and assume there should be a jump instruction. So it kind of simplifies things there quite a lot. And that's what a lot of other architectures also do. So I should have just done it in the first place, but I've done it now. Okay, so yes. And finally, probably the most important one is that I refactored the trap mechanism to use registers instead of function calls. So this is something that that I talked about quite extensively in the last episode, and I chose to do it in kind of the shortcut way that's not really simulating the hardware. I chose to do it in that way because it would illustrate all the concepts. So, for the purposes of people following along with this series, it's a useful way of kind of just understanding what's happening and kind of what the interactions between different modules are. But it's not the true hardware way, because in hardware we can just kind of put stuff in registers, and those registers are read and consumed and run through logic by other hardware modules, and kind of we need to do things in that way. So what I'll do is just do a quick git diff on this. Can I do it from here to this one? I should be able to. So yeah, basically just added a bunch of registers, and let's have a little look here. For example, in the main thing that happened is I added registers to indicate certain actions were happening, and I moved most of the main logic that dealt with that into, let's see, where is this? I'm not seeing the changes I would have expected here. Well, in any case, maybe I can actually just show the some of the code here. So, for example, in the trap module, we have a bunch of registers now. We have like set PC, PC to set. We have a couple of functions that we can call, which are basically like, this is also how we are doing like inter-module, like this begin trap. This is us getting a value in from another module, and this is how we've been setting it up in everything. So each module, if it consumes values from others, it's calling a function to get the latest values. So this is just a mechanism to read the latest value. And what we do here is we're reading two signals. One is called begin trap. So some external source is saying to the trap module, like, hey, you need to start doing your trap thing, basically. And there's another signal that says begin trap return. That's basically, okay, do the undoing process of this whole thing. So we can read those signals in. They actually come from the main kind of overarching hardware module, which is the RV32i system. And that now also has a bunch of, it's got its own register bank, and it has a few signals here. The CPU state and the pipeline state, they've been turned into registers themselves. And essentially, we're like, you can see with begin trap, we're actually reading out if there's a trap from the memory access stage, which has that itself in a register, and we're just sort of linking those two things together here. So that's also what a parent hardware module would do in like Verilog or something like that, or in Gateware TS when we come to that. And here we have some sort of values that are not registers. They're more like combinational signals, and we'll see more of what that means when we come to it. But basically, these are things that they take on the value immediately. There's no clock involved. They're just always kind of up to date with the latest signal, and it's kind of a computed signal, if you will. So it's one that I've put in here. And basically kind of all the hard work is now done in the compute function of the RV32i. It kind of does all of the interleaving logic of kind of checking things together here. Yeah, so it's basically, instead of just running these pipeline stages like we were before and kind of changing state as we go, now we're actually also doing some logic like, hey, do we need to take a trap now? And kind of going through all the logic, like reading the mcores MEPC out of whichever module caused the trap. In this case, there's only memory, the memory access stage that can cause traps to happen, but that will change in the future, of course. Yeah, this is pretty much it. And if you want to take a deeper look into that, of course, the code is online. You'll find it linked below. You can go through commit by commit, and you can see actually what happened in these wow, this word is escaping me. In the interluding time, basically. Okay, let's actually get to it and start building the reset mechanism. I think that's the simplest place to start. So, as I mentioned, the reset mechanism, it's a signal that comes into a register, basically, that says reset, and it puts the register back at its initial value. So what we're kind of going to need to do is to go into the register class itself and add a reset function. And what we're going to want to do here is actually keep track of this initial value, and then whenever we get a reset, both the value and the next value are going to go to that. They're going to go to that value. So we're going to say actually that This is going to be what's called an asynchronous reset. So we're basically setting the latch immediately when it comes in. You also have synchronous resets. So if we got a synchronous reset, we would basically set this and kind of, I don't know, I'd like mark something up here that said that yes, definitely on the, like, don't take any other values for now. Like on the next one, you're going to do a reset. But yeah, I'm just going to do it as a kind of asynchronous reset because it won't make a difference in this case and it's easier to build. So let's keep track of a, let's call it the default value. And we'll say the default value is 0. Value is actually the default value here. So let's say this.default value equals value. And when we take a reset, we're going to say this underscore value is going to be 0. Oh no, these are, of course, so reg index next is this.default, and then this.value is default. Okay, so this basically, whenever we call reset, we set back to the default value. Pretty straightforward. Then, since all of our registers are basically used in this register bank abstraction, let's just add a reset here as well. So reset, and what we'll do here is we will go through all of the registers that we have and we will reset them. So object.values this.registers, so just the values of all of them. For each of those, r.reset. So now we just call reset on all of these. And then I think what would be the most useful is to add a reset to the pipeline stage. Actually, I guess we could just write an implementation here, which would be this.regs.reset. Yeah, that should work fine. I don't think we're going to need to put anything special into any of the specific classes since they're all going to use the register bank. So I think we can just implement this here on the base class. And that means now that all of these stages have a reset. And why do we want to do this? Well, I think that because obviously between making these videos, I sort of move ahead a little bit and I work out kind of where I'm going with it and what the next video is going to entail. And I think when I was messing around, I found that basically taking a trap can result in a hazard in the pipeline. Even though we don't have parallel pipeline yet, right? We can still encounter kind of hazardous situations. And one of the hazards is if you're on a branching instruction, i.e. you're going to do a jump somewhere, if you take a trap, we kind of flush the pipeline. In our case, what flushing the pipeline means is that we simply put the pipeline stage back to instruction fetch. But the problem is that instruction fetch in the index file, like that reads a signal called get branch address and get branch address valid. And so what you can notice is if we were going to branch and the execution stage had a branch valid, well, it's going to use that address. If it's going to use that address and it's not going to use the trap address that we want to set it to. So this is a problem. It's one that's quite easily resolvable because basically what we need to do is when we take a trap, we need to flush the pipeline, basically. After we've read the values that we want to read from like the ME cores, the M cores and the MEPC and that kind of stuff. Yeah, so here we're reading those values. And what we also are going to want to do in this case is just say, let's add a reset to the whole system. Actually, you know what? I think I'm just going to reset them inline. Because there might be some things that, of course, we don't want to reset for everything. Let's just do it like this for now. We just reset these modules individually. So instruction fetch. Is this going to cause problems? In this case, no, I think. No, I think this should be okay. Let's try it out. So instruction fetch dot reset, and we're just going to want to do this for our modules. So decode, execute, memory access, write back. Okay. So I think that is all that's going to be involved. Yes. We need to bring the CPU in a reset state. That's the way. Yeah. I think this is probably all we need to do for this. So I think it's probably worth testing this out a little bit. We can write a reasonable test for this by, I say write a test, I don't mean write a real test because that would be too actually useful. Let's just make an exceptional case. So we're going to, yeah, because what's going to happen, right, is let's just try this out. Okay. Yeah, of course, but this is, so okay, the last instruction would have been a jump to start, and then this one should be something that causes an exception to happen. So let's load into A0 an unaligned address. Let's actually do this. And then we're going to want to run in the debugger. So we're breaking on start. Yeah, this should be good. So what I want to do is I want to just, whoa, that's really weird. I've never seen that happen before. What's going on here? That's really strange. Okay. Alright, so forget that, but in any case we're here. We go to start, and we seem to go into some sort of crash state. So that's not quite right. Alright, let's take a look at what's going on here then. So, that's interesting because I'm wondering if that even makes a difference. Maybe I just made like there's still some kind of bug here. I really don't know why this is why it's happening like this. This is not the really breaking into the so we end up getting here. We go into this. Let's see what happens inside the trap module itself. So we're in idle at the moment. So on the next clock cycle, we should read our begin trap, but we don't. Okay, it never seems to happen. So we're missing that signal. Okay, so let's take a look. where we're setting that signal. That's in the memory access stage. So again, run this. Memory access, and we should be seeing that happen here. So let's put a breakpoint down there. Trap. Okay, so we get to this point. It is unaligned. So we end up writing all of these values in, including trap itself. And what's going to happen now is that here in the, like every time we come to compute, what should happen is we'll be figuring out if we're going to trap stall. We are going to trap stall because the CPU state right now is 0, and that's not trap. But memValues.trap is active. So what's going to happen is this condition will now be met because we're in the pipeline state. We're going to move into the trap state if we weren't, well, in this case we weren't in it, so we're going to move in. And because memValues.trap is active, we're going to move into this this pot. So we're going to be setting the cores, the MEPC, and the MTVal. Then this condition won't be true because we don't have mReturn. And then we are descending in here. So what is the condition now? Well, what do we tell the trap signal is a begin trap if memory access value is out, trap signal is active. So that's what we would expect here in begin trap. So in this case, it probably won't happen on it shouldn't happen on this clock cycle because actually it should happen on this clock cycle because we've seen it happen. So let's dive into this. So we're going to go into this, get memory access values out. So let's just go one more in. Yes, this is not going to be the clearest way. So let's go back out. And then can we see at this point? Unfortunately not. Okay, so we're beginning the trap in this case. So we're going to be, that was strange. Did we set this value? This.state, next value is 1. Okay, so we should be moving into this part of the trap handler. So now this time around, this time we're not in the pipeline state anymore, so we don't enter here. We are in the trap state, but we're not yet returning to pipeline mode, so we should skip that. And in this case, we're not returning, so we should skip that too. And when we bring ourselves back to the trap state, we should end up. Okay, so for some reason this time, that's different. I think something's up with the debugger here. All right, so we're gonna bring in those values into the CSRs themselves. We're gonna figure out the index where we're gonna jump to. So the exception number is 4. It's not an interrupt. The offset is going to be, depending on whether it's an interrupt or not, well, our offset should be 48. And then we're going to go to whatever the base vector address is, plus the offset, plus the index shifted up by 2, so basically multiplied by 4. So the PC value we're going to end up with is this. This number is this address, so that's 100 with 44. And let's actually open up another terminal. And yeah, let's put it here. And what we'll do is cd into, well, we're already in system code, so let's do RISC-V object dump main. And so that address is here, which is telling us we should be going into this handler called ISR exception crash. This is in fact the correct, I believe that is the correct one. So let's just actually take a look, isr.c, and we'll see down here, like order wise, it comes between one of these. So we have exception, 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 default, and then exception, and we're going to that one. So we have here exception, 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 default, exception, load address misaligned. So that's looking good right now. And then, so we're saying that we are going to set the PC. So that's our kind of control signal in that case. We are going to return to pipeline mode, and we're going to go back to idle. So we're not going further with this until until the main module is taking care of it. We don't set the PC ourselves, we just write a register, and then the main module will read that register and set the PC itself. Okay, so now I believe we still have a breakpoint up here, so we come back here, and we're still going to be in trap store. We're not in pipeline mode, so skip all of that. This time we have return to pipeline, which is a 1, so we should come in here. So we're going back to pipeline mode, we're going back to instruction fetch. We are going to set the PC in this case. I think this should always happen in this circumstance, but yeah, I have this if statement anyway. So here we're setting the PC with the correct value. We're also setting PC plus 4, which is quite important because of the way that the PC gets its next address. And then finally, we can recompute. We go into the next stage. And so what I want to just check now is, well, actually, this should just go to the next instruction. And it did. Yeah, so I'm actually not really sure what went on before. But we need to go through a few of these, and then we're in exception crash. Okay, so that seemed to work. And now presumably the reset part will also work. We'll try that out. Of course, this is still happening for whatever reason. So here we ended up there, we got unaligned. Good, wait. So it does seem to be whatever I just did, the reset, that's actually causing this. We shouldn't need to read those signals further than that. But that is what's happening. So that's interesting. I guess let's follow it through once as well. Unexpected debugging, but I think it's good to go through this stuff and for you to also experience these kind of problems, because this is a lot of what is involved. Actually, there's something that in the coming episodes, maybe in the next couple of weeks, I would like to maybe do a stream actually building a sort of even more advanced debugging tool. I've actually built this already, but I think it's not quite fun to show it. Not part of the main series, but maybe as a stream, and I'll just post it into the series as well, and people can watch it if they like. Basically building a waveform viewer for this, so we can kind of get a macro view of the whole thing. Alright, so the exception is going to take place. So let's actually go and... Not the memory map, I do that quite often. let's put our breakpoint in here. It happens. That's great. And then let's go to the trap state as well. And just start watching this whole thing. So at this point, we haven't latched the value, but in the next clock cycle, we should be trapping, although it doesn't seem to happen. Oh, and it's because yeah, but we haven't reset yet. This is strange. Let's put a breakpoint here. Take this one out for now. Here we get the exception, so we'll put this back and memory access. So here we are setting these values. And here we get to this point. So now we have the trap signal. I guess the problem with this is that we're actually, we're nuking this trap signal before it's actually had a chance to propagate. So maybe we actually also want to maybe we actually also want to buffer this signal up by 1 so we can pass it on. It's interesting because I don't think this is how I did it before. Okay, yeah, I think what I did before was I had an explicit signal in the trap itself to cause the flush. So it would be the trap hardware that would initiate the flush, kind of like the whole reset. I guess we can do that. That will work as well. So let's inside trap. We'll have a new signal, a new register, and it's going to, just like set PC, which is just like a true false kind of signal, flush will be as well. And what we're going to want to do at the point of, I guess we're going to want to do it at the point where we get to here, because we already have these values. Will this be adequate? So that's if we're beginning the trap, and then basically any other idle time, we actually want to reset that signal because we don't want to flush all the time. So that's that. And I guess what we could do realistically is just decouple all of this. So we'll just make it an additional step down here. So if this dot trap dot flush dot value, I'm missing a stage here. Now, actually, I think the trap needs to basically set this off like in any other stage. So we set it here, but I think if we're inside this state, then we're also going to want to do it like we're going to want to set it off. If we're setting the PC, we're not going to want to be flushing. If we're returning from a trap, I guess we're also not flushing there either. An interesting thing to note, like from a hardware perspective, and you need to remember, like, even though we're sort of writing code here, and we're writing a switch statement, like, this is going to turn into an actual electrical circuit. Like, that's the basis of hardware, right? And things like if statements become multiplexers. Switch statements too, they also become kind of multiplexers, which have some sort of controlling value that says, like, you know, it's exactly like this. Like, this is our controlling value, and depending on what that input is, we take one of a series of signal paths. It's a switch between a bunch of different things. Literally, it switches on and off which signal becomes on, which activates some part of the circuit. So this part will be active, this part. And the registers, of course, like, they're receiving a value on every clock cycle. Either we're updating a value or we're keeping the old value, so to speak. So what happens is, even if you don't set something explicitly inside a like one of these conditions, like if we have a register here that we're not setting, like we're not setting PC to set up here, kind of implicitly in the hardware, this signal, or this kind of value, which is a collection of signals together making a binary value, this will get set back to itself. That's kind of what will happen. So every value is always explicitly set in hardware, right? Every clock cycle, that register is kind of receiving its next value, so to speak. So it's either implicit or explicit. So I'm just thinking about being explicit for the case of, like, making sure we don't multiple flush, but I think we have it here. So let's give it a try, I guess. I think the easiest thing always to do is to just, like, let it run through without catching any breakpoints. Okay, so that looks good. And then we go into the exception. And one of the things I did here was I actually wrote this exception crash handler because, and I should have mentioned this in the beginning, in the last episode I said we were going to write the kind of recovery mechanism code that you can do for unaligned accesses. And I decided against it because I actually want to focus on really finishing the core of the CPU so we can actually move on and continue the build. And this was a sort of side quest, so to speak. And although I think it's interesting, I think it's better to keep the focus on finishing the instruction set and doing some of the other things we need to do. So what I actually did was I wrote this exception crash handler, which is shared by any exception that can happen. And what it does is it actually just sets the reads the CSRs into these registers. So into register A0, into A1, into A2. So we can actually read the state of the processor at this point and see what's inside these registers. So if I said we should be inside the RISC class here. So if I read the reg file and like we read register 10, which is A0. In A0 is the cause, so what we should see there is 4, I believe. That's what we get. And then we can read the MEPC, so that's kind of like what triggered this basically, and the MTVal, so the instruction that caused it. So if we're actually debugging this in the debugger, we still can get access to that stuff quite easily, even if we didn't have breakpoints all over the place when it was happening. So I think this is quite interesting, quite useful to do. Of course we could just go and read the CSRs ourselves, but this is like a nice debugging thing. Like, we just end up in this actually, you see this a lot in like microprocessors where you have hardware debuggers that you can plug in, and like there'll be a breakpoint instruction here which will stop in your thing, and you can actually go and read these values out as well. So I think that's just a small useful side note. Okay, so that seems to work. I'm happy enough with it. It took longer than I thought it was going to, so I think we shouldn't waste too much time around here. Let's take a look at mStatus, the mStatus register. So if we go to the spec document and we look at the privilege spec and we take a look at where do we want to look? We want to look in the mStatus register. Where is it now? I'm completely blind to this thing. There it is. Yes. We have these various kind of different bits inside this thing which are indicating something. So one of the things that we are indicating here is that we have the machine mode interrupt enable. This is like the global interrupt enable signal. What we actually do when we enter a trap or an exception or whatever is that we actually put this value, whatever that was before, we store it into this register, MPIE, so the machine mode previous interrupt enable. And what that does is it allows us to actually turn off interrupts when we enter a trap, because you actually, if you enter an exception or an interrupt or a trap, you don't immediately want something to come and mess up whatever you're about to do. That's clearly going to be important. So what actually happens is this gets set to 0 in that first instance. And if you want to actually kind of allow your, if you need to then be able to take sort of while you're in your exception, you know you need to be able to handle another interrupt or something that's going to come from outside, what you can actually do is store this bit off somewhere else yourself, somewhere that you know it's going to be, and you can set this back on, and then that allows another interrupt to come back in. And then what can actually happen is you will like when you exit that interrupt, you need or that interrupt or that exception or whatever happens that you kind of expect that could happen, you want to go and load this back at the end into your previous thing, and you kind of want to return, and that will return you back into the original exception handler. So it's this ability to do stacked up, like multiple traps in traps, basically. So this is something that we need to basically arrange. So when we enter this thing in, we want to copy the old value into this one. We want to set this one to 0. Not too difficult. Going to be a bit of masking and bit manipulation. So what I think we'll do is to put these as constants inside the trap module. So we want to export, and it's going to be so we're going to be dealing with bit 3 here, which is going to be mStatus machine mode interrupt enable. So let's call that mStatus machine mode interrupt enable, and this is actually the bit. So the bit number is 3, and then we want to make a mask for that, and the mask is just one shifted up by this bit. Right, and of course we also need the MPIE, which is bit 7, so it's just the same thing. We'll just copy these, and there we can set this one. This is bit 7, and this one also gets set. So now we can actually manipulate the mStatus register a little bit. Okay, I don't think we actually need these elsewhere, but I'm going to export them anyway, just for ease of use. So we're just going to do it in this whole section where we're already reading CSR, setting CSRs and that kind of thing. So we are going to say, how do we do this? So the 3 things we want to do, or the couple of things we want to do, is we want to copy the current MIE into MPIE. Then we want to set MIE to 0. So we want to disable interrupts at that point. That's actually it. So the current MIE, or I guess we could just call it MIE, like this. The current one is this.csr.mStatus. ANDed with the mstatus MIE mask. And then that isolates the bit, but it's still in position 3, so we want to shift it down by, we'll use this shift to make sure we don't, we wouldn't get a, there's no way for us actually, it's not possible, so we'll do it like this. This is going to give us the bit just as a 1 or a 0. We could have done this other ways, but this is the easiest way. Then what we want to do is actually set that. So we want to say that, let's get mstatus. We can do it like this. This.csr.mstatus. We would do this all in one operation in hardware, right? It would be like, we'll go through a series of logic gates and just do all of this operation all at once, but we can do it over a series of statements just to make it clearer. So what we want to do is we want to say, first let's like unset whatever's here. We need to make sure it's 0 because we can just OR in the bit, right? If we have this bit and we have 0 or 0, it will still be 0. So that's fine because that's what it was before. If there was a 1 in there before, of course, right, and we did 0 or 1, it's not going to overwrite that with a 0. So what we want to do is we want to create a blank slate. So we want to say that the way we do that is we take whatever is in there now and we AND it with the inverse operation, the inverse of the mask. So not this mask, but the MIPE mask. MPIE mask. So this basically selects, like right now, this would select one bit inside that thing. And by inverting it, we're selecting every bit except that one. So if we AND those together, it's like we're just going to grab every bit except this one MIP bit, MPIE bit. And because of JavaScript stuff, we need to do this operation at the end to make sure this stays as an unsigned number so that when we do further bit manipulations with it and we expect things, it behaves in the way that we would expect. And when we're reading debugging information, that kind of stuff, we expect all of the numbers in this system to be unsigned, and weird things could happen otherwise. So now we've actually unset the bit. Unset MPIE bit. Now we've done that, we can actually OR in the old one, so the old value. So we can say, and by the way, notice that we could just, no, because of this operation, we can't do that. So let's OR in, and also let's not do it here because then we can just do this again. So we will OR in the MIE shifted up by mstatus.mpie bit. So basically now we're taking whatever the value of this was, putting it in the position of that bit, and ORing those together so that we take on that value. And again, we're just making sure that JavaScript doesn't turn that into an assigned number. And finally, we want to unset the MIE bit. So what we were doing here is save MIE to, let's do it like this, MIE to MPIE. And then we want to set, let's get rid of that. We basically want to do this again to unset MIE. And then this time we do it like that. So we can do that. We can do these logic operations just in one step. We could make one expression out of this, but I think it's clearer to just set them up like this. And then when we're undoing a trap, when we're leaving a trap, we want to do the inverse operation here. So let's scroll down to when we do return from trap. So in this case, we want to, what do we want to do? We want to move MPIE into MIE. And then I guess we want to unset MPIE. Yeah, I think that makes the most sense. It's kind of like a real reversing of the whole situation, but I think you also don't, like, if we were to then return from another trap and we hadn't sort of accounted for that, I'm not sure about this. I'm actually not sure what we should do in the but I'm going to unset it anyway. I mean, someone can tell me if I'm wrong about that. I think we're going to unset this. So it's going to be really similar to this. So we'll copy it. So MPIE mask, MPIE bit. Then we are going to unset the MIE bit. So that's just this. Then we're going to save MPIE to MIE. Same thing again. Then we're going to unset MPIE. So that's it. So that's basically saving, or kind of restoring our previous context. So that's another item off the list, as it were. Yeah. All right, then we can implement the eCall and eBreak. So this is actually finally us implementing these 3 additional instructions. We've got eCall, eBreak, and fence. Now, fence is basically going to be a no operation. So fence is an easy one. Let's start with that. The easiest way, I think, is to go into the decode stage and to add a new register here. We've got all of these types here where we check is store, is load, that kind of stuff. I think what we can do is add another one. Is fence. I don't think we need to have one. We've got this is JLR kind of instruction here, but we could have that for fence as well. But let's check. The way we check if something is a fence instruction, and I think we should take a look at the spec for this, of course. The way we actually check if something is a fence instruction is if it matches this bit pattern. So there are 2 fence instructions actually. There's one here where we specify a predecessor and a successor. And I'm not even going to talk about what fence is. I think I briefly went into it in one of the other videos, but since it's going to be a no-op for us, let's just get through it as quick as possible. Basically, we just need to look at this opcode. So if it's this opcode, then we're ignoring it. And that's the same for both of them. And you can see that in this other case, it's just all zeros, and this one has a predecessor or a successor. So not super important for us. So when we're checking a return from trap, which is this is an mret instruction. So return because we don't explicitly check for mret, this is just a signal now that that spits this out. The mret instruction, what that does, right, is it checks if something is a system. Oh no, fence actually doesn't use the system code, does it? I'm getting myself confused here. No. So for a fence instruction, we do need to check its. So this dot is fence dot value. Pull to int this dot opcode dot value, next value rather, is if it's this, then it's a fence instruction. And all we actually really need to do now is we need to come down here and we want to find this place where we're basically no-opping. And yeah, we can no-op on the is fence. So that's also a no-op. And then as we move through the pipeline, like the fact that this is a fence and nothing else is going to mean that we don't activate any logic that would be doing something useful in the processor, simply because we didn't activate anything. We don't have an immediate value, we don't care about anything. So just by the fact that we did this and we're not kind of throwing an error, this should actually be an exception, by the way. But the fact that we do this means that it will just go through as a no-op. So that's great. I think that's actually all we need to do. Now, eCall and eBreak. These are, now there's a little bit more to these ones. So in eCall and eBreak, if we go back to the spec here, they're actually system instructions, which means they have this system opcode. So they have the same opcode as the CSR instructions, for example. But an eCall, we recognize that basically everything here is a 0. And for an eBreak, the 12-bit immediate is a 1. So that's the difference there. That's the way we identify these. So first, let's just identify these instructions. Now, this is what I was thinking of before. I was getting myself confused. They share a lot with this mret instruction, right? Because a return from interrupt instruction is encoded in a very similar way. The only difference actually is that the return from interrupt is looking at a particular immediate value, which is hex 302. And we're looking at a particular immediate value, which is either 0 or 1 in these cases. And notice these are checking 0 and there's other places. So what I actually want to do is to call this some generic name, and I'm trying to remember what I called this before. It's going to take a look. Yeah. I called it system instruction base. And the system instruction base is just doing this stuff. So let's do it like that. And what we can now do is to like just plonk this in here. So I think even let's put those on like a line here. So if these two conditions are met, then it's an mReturn. And in the case that it's an, let's check for first eCall. So I think what we're going to do here is have is eCall. That's going to be bool int. I guess it doesn't matter if we do bool int here. We could actually just say, is it a system instruction base? And is the I immediate equal to 0? Then it's a call. I guess we can do it like this. Is eBreak. In that case, it would be equal to 1. And what we actually need to do now is basically what we do in the memory access stage. And again, I should have mentioned this, but like if let's actually search for eCall. Yeah, all the way back here. The eCall instruction is used to make a request to the supporting execution environment, which is usually an operating system. The ABI for the system will define how parameters for the environment are passed, but this will usually be defined in locations in the integer register file. Basically, eCall is kind of like software interrupt in x86 and that kind of stuff. It's a way for us to go from like one privilege level into the kernel, and the kernel will look at like some of the stuff we've passed and decide how to like proceed from there. It will do something behind the scenes and return back to user code. And we're not going to have any of that kind of stuff, at least in the beginning. We're just going to have a simple bare metal processor. So the idea of a system call is not super useful. We could use this for something else within our processor, right? It could just be a way of doing some, I don't know, we could use it for some other kind of real-time operating system-y kind of thing. But yeah, we don't actually need something like that. So basically what this does is, and you'll notice it doesn't like further specify it, but if we look in the privilege document and we look down here at the mcause table, you'll notice that there is an environment call from mmode. So basically we're going to just put, like, we're going to activate this trap handler. Basically we're going to just call a trap function, and it's going to be number 11, and it's going to be environment call from mmode. Right, I guess we could wire all of these up, but I'm going to hardwire this to mmode for now, and that should be it. So I think what we can do is we can take a look at memory access and we can see how it's done. And what we can see is that we have these 4 registers. Remember, before this was a function call, and now what happens is I add 4 registers and a signal that says this is a trap, and that's it. We look at that signal somewhere in the main overarching parent module, and we kind of proceed from there. So it's just going to be the same thing. So I'm actually just going to copy these registers out of here. I'm going to dump them into decode, like this. And what we're going to do is we're just going to check, like, if this isn't equal, it doesn't matter which one we look at first, they're going to do pretty much the same thing. Then let's even just copy the rest of this, like it's only a little bit is going to change. So mcause, and the actual one that we want to have is environment call from mmode. And I guess we could return, yeah, we want to return kind of to the next instruction. And the empty val, well, that's like kind of like, that would be our argument in some way. Probably we'll also use the registers to, like, this would be a call, right? So I think we can just set this to 0. I think we don't need to do anything with it. And then we return. We don't actually need to return, or just like we don't need to return in the memory access stage, but I'm just going to leave it in there for now, and we'll probably clean that up a bit later. And if it's an e-break, I mean, it's almost the same, but this just becomes a breakpoint. And of course, like a breakpoint, that's actually quite a useful thing for us to have. Like, we might want to actually, like, not necessarily go into a trap handler. We might want to do that anyway, but what we might want to do is just put a break, like kind of break in the execution environment inside the debugger, and then that's kind of a useful way of just breaking. I mean, maybe I'll even do that actually. I might debugger. Yeah. Cool. But actually, you know, I think I'm just going to implement it like that. I think I'm not even going to... Yeah, I think I'm not even going to do this for now, because this is just the more useful way of doing it. Whoop. Yeah, this is actually not an integer value. It's a weird way of doing this, but it's fine for now. So I think, yeah, I'm just going to, I'll leave that in as a comment. Maybe I'll just comment return as well. But this is just going to give us a debugger. We're just going to, like, get a breakpoint at this point. And that's quite a useful thing to do, I think. Okay. Now we need to actually handle this, though, because if we go back to the parent module, and the way we tell the trap module to begin a trap is just by looking at the memory access out, which is not enough. We actually need to like kind of OR together all of the possibilities for this. So the current 2 possibilities we have are are these two, right? Trap is not yet exposed. That's true. I need to expose it from here. We're going to need to expose the other ones as well. So let's copy those from here. Like that. Okay, that now works. So like we'll know to begin a trap in this case. But also we have some logic here that's going to deal with like where we end up getting our M-cores, MEPC, all of that kind of stuff. So here I have this to do like a better multiplexer abstraction, because what we're essentially going to do here is instead of having a like memory values out here, what we want to have is like kind of a generic values, and if there's something in there like where we should be trapping, then we're just going to extract these values from that thing. We're kind of like multiplexing them together. But actually we're going to, I guess this is more of a priority encoder than a multiplexer, because like if two things are saying take a trap, maybe we want to take the thing which is furthest in the pipeline. So we want to prioritize stuff that comes from later pipeline stages because it's instructions that happen earlier. So I think what we will do is to do something like this. Let values equals, call it trap values. Yeah, trap values is null. And then we will say, because I'm not going to build the whole multiplexer abstraction now, or a priority encoder, because we can just do it with an if statement. And that will do for now. Otherwise, yeah, this episode's going to get way longer than it already is, and it's already long. So if, yeah, let's do that. We've got the mem values. We're going to have the decode values. So that's going to be decode values. And I'm kicking myself for not making these all the same name. Decoded values out. mReturn and trap stall. Well, now we also need to bring in decode values dot trap there. So there's that. And what we want to do is to say if decode values dot trap, because that is something, wait, no, mem values is later in the pipeline, so we want to look there first. If mem values dot trap, then trap values equals mem values. Else if decode values dot trap, then trap values equals decode values. And then because TypeScript is smart enough, it will actually understand that if this is not null, then there will be valid register values in these. Does it understand that? It says any. I expected it to figure that out, actually, because these have overlap, and I would expect that it would figure out the overlap in the types, but it is not figuring that out, which is surprising. Put this here. Does it change anything? No. Huh. It's not. It's also not complaining, but I thought it would actually pick this up. Let me take a look back at whatever I did before and see how I did that. Oh yeah, okay, I know what I did differently. In that case, I didn't do it like this, but instead I did it as like a ternary. And then that case, in that case, everything is defined. So this is kind of a weird ternary, but I think it's like the best way of doing kind of like else if. If you have something that like prettifies your code, then this kind of ternary formatting is like not going to be pleasant for you, but I think this is the most straightforward way of doing it. And then these should be defined now. It now is defined because it understands that there is a crossover now between these two things. Good. And let's get rid of the to-do because I'm not going to build a better abstraction for that. Okay, so the easiest way to test this now is just to write some C and trap into these different things. So let's try equal. So let's go into CRT0. No, let's do it in C. So let's get rid of that and let's put it in the main function. Main.c. Yeah, all right. So I believe it's just going to be equal. That's it. We don't have any of that stuff. We don't need to initiate a result. Let's do it after this write, because then we'll also see it going like that. And we also need to edit the ISR because I want to make something that's not the default. So let's have an ISR for, let's call this well, equal exception. Oh, we could just call it equal, right? So what we're going to do here is, I don't know, it doesn't really matter. I guess we could just yeah, let's just make a UN32A equals 55. That will be easy to see. I think by their nature, like, ISRs are kind of considered volatile, and it wouldn't optimize this out, I think. I might be wrong about that. But in any case, we'll see this in the generated code. Also, I'm not building any of this with optimization levels at the moment, so it wouldn't make a difference anyway. So let's make that rebuilt CRT0, rebuilt main, rebuilt ISR. Okay, good. And let's have a look at the output. So here in main, the equal instruction is down here on 164. And we've got the equal exception, that's at 118. And we can see we load in a 55, so it should be easy for us to see that. All right, good. Good. I guess since we're not actually like breaking anything here, we could actually build in we could actually build into main that we did a break after this. Yeah, why not? Let's also do that. So let's do make and preview the code again. So we're going to do equal, we're going to go into the handler, do all of that, and then we should break and we should find ourselves in the thing. This is fun. Let's try this out. Hopefully this all works. All right, got this nonsense again. And where are we at? I'm hoping to not need any breakpoints. So let's turn these all off for now. So we're in start, because I put the breakpoint in start. Actually, let's make a breakpoint in main, because we want to just jump through all of this first, I think. Hopefully we get as far as main. Still breaking in start, that's interesting. Why is it doing that? Maybe because I've told it to be in step mode already? Oh, here we go, we're in main. Alright. Good. So, we do a bunch of stuff. We write into a particular address. Then we're going to do equal. So we should end up going into the whole trap handler business, which we are. although we're going to the wrong one. So here we're going to address 60. Okay, so where did we end up then? We should have been... No, that's probably correct, because I didn't actually update the table. So that probably is correct. Environment call from M mode equal. Yes, it helps. So rebuild, jump in here. Alright, so equal. Now we're jumping to equal. We're going through the instructions. There's our 55. There's a no op. And then we're going to do m return. Hopefully this still works. Yep, then we're in e-break. Excellent. So then we've got a hardware breakpoint here as well. What we might want to do is kind of make a signal for this so it stops like before the next instruction. Yeah, I think that would be the most useful, because now you're going to need to go through each subsequent instruction and everything. But this is already great. I'm happy with this. So, oh, unknown CSR 1. Yes, because it's going to consider that to be a CSR instruction. So, what I said previously, where like, oh, we don't need to return after this. Yeah, because this is not going to get caught here. This is going to get caught on the is system part. Where is that happening? It's going to happen when it's a system instruction doing CSR stuff. So let's actually just return at that point. No, it's still going to break stuff, isn't it? Yeah. So what we could do is we could go into the whole breakpoint anyway. Yeah, I think what we want to do is set some kind of flag here. I'm going to leave it for now. I'll come back to that and fix that up before the next episode. But yeah, so we now have every single instruction that we need to implement. This is a big thing. We have every single one of these instructions now. And they all hopefully work correctly. And yeah, we can actually sort of continue from this point. There's one major thing left that I want to tackle, and that's what we're going to tackle in the next episode. And that's going to be making the memory bus, the system interface, making it asynchronous. Or maybe asynchronous is not the correct term. Maybe it is actually, but we want to make it so that that bus interface can take multiple cycles, right? If you try to do a read into memory, there's some chance that it might take a few cycles to come back. That's pretty normal. And when you do a write as well, maybe it's going to take some time for that to happen. And I want to simulate that inside the design, because right now we have the same problem everywhere that we're reading memory that we did with the previous trap interface. And that is that we're doing that by calling a function. So if I go into memory access, right now, you can see we just, we do this at some point. Value equals bus read. And in hardware, there are no functions, right? And they don't execute immediately. So this could never happen. So what we actually want to do is when we're going to do a read, we need to just set a kind of a signal, like just like we set the trap signal to initiate a trap from kind of outside our own module. We're going to set like a memory read signal, and then we're going to have an address that we're going to read from. We're going to put that into a particular register, and yeah, and maybe some of the other things that we need to say about that, like the memory access width. And then we're going to have to wait in a state where we're waiting to receive the memory data back. So we're going to be checking another signal and seeing like, oh, is our data ready? It is. Let's move on and continue with the pipeline. And in order to do that, we're going to have to create a whole bunch of state machines, which we have some experience with now. We built state machines for the pipeline in general. We built state machines we built a state machine in the trap module. And what we're going to have to do is basically make every single pipeline stage its own state machine. And also, we're going to have to do some work to make sure that the progression of pipeline stages actually works correctly. Because right now, we assume that we move each clock cycle to the next pipeline stage, which won't hold true in the future. But that is for the next episode. And when we have that, there are little bits and pieces and small things to fix up and kind of, small things to address. But once we have those pieces in place, I think we've taken the emulator as far as we need to take it in order to proceed with the actual hardware design. Because if we can do everything that the emulator can do in hardware, I'll be extremely happy. All right. Thanks for joining me on this one. Thanks for staying patient and debugging this issue with me. And if you have answers to any of the questions that I've asked during the course of this whole thing, please feel free to leave those in the comments. Thank you to all the Patreon subscribers, or patrons, I should say, of the channel. You kind of make these kind of videos possible. You make it, it's a great signal to show that this is just worth doing for some people. And you enable me to get a hold of the hardware and the materials and that kind of stuff to actually do the research. And that's not always hardware. Sometimes that's just books and things like that to actually, dive deep into the resources so you don't have to necessarily. Although I advise that you do because it's a lot of fun. In any case, I wish you a great day and I will see you next time.